Hi, it's Jordan again for pretty much my last experiment here that I've done in general chemistry at Doane University, and I'd like to talk about DIY kinetic sand and how I made it. So I started off with dish soap, blue art sand, about 4 tablespoons of cornstarch, and some mortar. And I'll show you exactly what I have left, and show you that it stretches too, breaks a little bit, just a tad bit. That's because there wasn't any slime in there, but it stretches and sticks together like kinetic sand is supposed to. So now I'll go more into the science behind what exactly is happening. I would also first like to show you the materials that I used. And here is the exact sand I used. And of course my dish soap came from here. It's clear dish soap. And here's my cornstarch that I used. And then I just used water from my sink for the water that was needed for the experiment. Now I'm actually going to move on to the science behind the DIY kinetic sand. So kinetic sand can act as a solid and a liquid at the same time, but how exactly does that work? When it's held softly, it oozes out of a person's hand and flows to the ground like a liquid. Yet, when it is held and squeezed tightly, for example, if a person holds and squeezes it and puts it in the ball shape, or at least attempts to, then it maintains its ball shape from the resulting squeeze instead of flowing like a liquid when only held softly. Why is this exactly, though? The reason is because kinetic sand is a non-Newtonian liquid, meaning that it behaves differently than most other substances. It is a dilatant, which means that the viscosity or thickness changes when shear strain is applied. And to be very specific, the mixture is 98% sand and 2% polydimethyl siloxane. And a dilatant, also termed shear thickening material, is one where viscosity increases with the rate of shear strain. And such a shear strain thickening, also known as the initialism STF, is an example of a non-Newtonian fluid. This behavior is usually not observed in pure materials, but can occur in suspensions. A dilatant is a non-Newtonian fluid where shear viscosity increases with applied shear stress. And this behavior is only one type of deviation of Newton's law, and is controlled by factors such as particle size, shape, and distribution. The properties of these suspensions depend on Haymaker theory and van der Waals forces and can be stabilized electrostatically or sterically. Shear thickening behavior occurs when a colloidal suspension transitions from a stable state to a state of flocculation. A large portion of the particles of these systems, and as well as properties, are due to the surface chemistry of particle dispersion known as colloids. This can be readily seen with a mixture of cornstarch and water, sometimes called oblek, which counts as a counterintuitive way when struck or thrown on a surface, and sand that is completely soaked with water also can behave as a dilatant material, but in my specific case I added sand and water and dish soap, as well as cornstarch. But just plain sand with water can also act as a dilutant material. And the reason why when walking on wet sand, a dry area appears underfoot directly is because of these properties, and because it is a dilatant. And also, I'd like to explain that rheopecty is a similar property in which viscosity increases with cumulative stress over or agitation over time. However, I'd like to say that the opposite of a dilatant material is a pseudoplastic, and also rheopecty is not to be exactly confused with dilatancy. Even though both properties have increased viscosity as a result of applied stress, they are quite different. The difference between dilatant and rheopectic is that materials that are rheopectic materials have viscosity that's time-dependent and thus increases the longer stress is applied, whereas dilatant materials' viscosity increases just with an increase of stress, and it's not time-dependent. And I'd also like to mention that there are two types of deviation from Newton's law that are generally observed in real systems, and the most common deviation is shear thinking behavior, where viscosity of the system decreases as shear rate is increased, and the second deviation is shear thickening behavior, where as shear rate is increased, the viscosity of the system also increases. And this behavior is observed because when water crystallizes under stress, it behaves more like a solid than a solution when that occurs. Thus, viscosity of a shear thickening fluid is dependent on shear rate. The presence of suspended particles often affects the viscosity of a solution. In fact, with the right particles, even a Newtonian fluid can exhibit non-Newtonian behavior. And a number of non-Newtonian fluids can be found naturally, although most of them are pseudoplastics as opposed to dilatants. A famous example of a non-Newtonian fluid is quicksand. At first it seems to be solid, but as the victim walks onto it, thereby applying stress and causing it to be more viscous. With quicksand as a pseudoplastic, they sink as they struggle, applying more stress to quicksand, which causes them to sink faster. Another example of a pseudoplastic is ketchup, which will not flow until it is squeezed or shaken. There are not as many natural dilatants, although certain proportions of sand and water mixed together can display dilatant properties. For example, at a beach, if you stand on the wet sand, your feet will sink in slightly, but if you run across the sand, thus applying greater stress to it, it will behave as a solid, and your feet will not sink in. A dilatant fluid can easily be made by making a 2-to-1 mixture of corn flour and water. It is a liquid, but when stirred, it becomes thicker and more difficult to stir, and if hit with a hammer, it will shatter like a brittle solid. But if left alone, it will return to a liquid state. That's about all I have to say regarding non-Newtonian fluids in this project. Thank you for watching my previous videos. I hope to do another video in the future. Thank you and good night.